So today we're going to be doing 115, which is solving three variable systems algebraically. Okay? So our essential question is, how is solving a three variable system similar to solving a two variable system? And we're also going to be talking about solving planar systems using a combination of substitution and elimination. So oftentimes when you're solving three variable systems, you're going to be using a combination of substitution and elimination. You're not going to be strictly using one or the other. Oftentimes, you totally can, but sometimes the easiest route is to kind of mix them together. So let's talk about what a three variable system is. So up to this point in your math career, you've basically only been talking about two-dimensional shapes, two-dimensional things in math. Okay, in geometry we talk all about two-dimensional things. That's like the Cartesian coordinates that you guys are used to dealing with, x and y. Now we're adding in a third dimension, z. So this is more realistic to real life, okay, because things have depth in real life. We talk about height, we talk about width, but now we're talking about depth, okay? So that's what that really means. And your ordered pairs are going to have three coordinate pieces instead of one. Or sorry, instead of two. There's not one in any case. So when you solve a three variable system algebraically, three things will happen. The first thing that will happen is you'll get an ordered triple, and that means you have one solution. The next thing that can happen is you'll get a true statement such as 0 equals 0, which means that you'll have infinite solutions. And the last thing that can happen is you get a false statement, which means we have no solutions. So before we go on to the next page, I'm going to pass out. Okay. So continuing on, let's look at the first example. So we have a system of three equations in three variables. So as you can see, we have three unique variables, x, y, and z. And the first thing you always want to do is to look and see if you were to add any of these two equations together, if there's any variable that would go away when you do that. So does anybody have any suggestions? No. Good. Y in the first and third, right? So if you look at your first and third equations, if you were to add these together without doing any scalar multiplication, you would already cancel out a variable, right? Mm-hmm. So let's go ahead and do that first. So I'm just lining these up in terms of like terms, and I'm going to be adding these two together. And this is 1x minus 3x, which is negative 2x. Good. What happens to my y's? Good. And then 3z minus 2z. It's just z equals 7 minus 10, which is negative 3. So that's what we end up with when we do that. Now, that's usually the best way to approach the problem to start, is if you can add two together and cancel out a variable right off the bat. That's probably the best first step. Now, the other goal would be, now you want to try to get another equation with the same two variables left, x and z. So we want to try to cancel out another set of variables. So what could I multiply this middle equation by so that I could add it to the first one to cancel out the y's? 2. So if I multiply the middle equation by a positive 2, that's going to allow me to add it to the first equation, which would allow me to cancel out the y's. So I distribute, I get 4x plus 2y plus 2z equals 8, and then I'm going to rewrite my first equation down here. That's x minus 2y plus 3z equals 7, and I'm going to add these together. That's going to give me 5x plus 5z equals 15. Yes?
Why did you multiply by 2?
The reason I multiplied it by 2 is because I knew if I multiplied it by 2, I could add it to the first equation, and if I did so, it would cancel out my y's. Okay? So now I just basically have a system, a two variable system now. down to two variables, right? I have x and z. So you can either at this point use substitution or elimination. Okay? What do you guys prefer? Yes?
I don't know which equation to pair it the second one with. If you did the middle and the top one, could you have done the middle and the bottom one? Not the third one?
Yeah, so the reason I did the middle and the top one is because I just multiplied by 2, but you could have, like you said, if you multiplied the middle one by -2, you could have added it to the bottom one, and that would have been another correct solution. Yeah, so your goal is, once you get one of the equations to have like x and z left, you want to get another equation to also have x and z left. So you can do that by several different means. Any other questions so far? Okay, yeah, so there's going to be a lot of ways you can kind of go about these. So from here, do you guys want to do substitution or elimination?
Substitution.
All right, let's do substitution. So in this case, I see that I can get my z by itself pretty easily, right? I can do that by doing what?
Add the 2x.
Good, I can add the 2x to both sides. And when I do that, I'm left with z is equal to 2x minus 3. Now that I know what z is equal to, I can plug that into my other equation. And you could have also done elimination here too if you preferred. So that's going to give me 5x plus 5 times 2x minus 3 equals 15. I'm going to use the distributive property. I'm combining like terms. Add my 15 over. And that gives me 15x equals 30, which means x equals 2. Good. So I found that x equals 2. So far I know x equals 2, and then I know I have to find z and y as well, right? So anybody have an easy suggestion to find z? Good, I can use this equation right here, and I can plug in the 2 for x. So that's going to give me z equals 2 times 2 minus 3, which means z is equal to 4 minus 3. Z is equal to 1. So now we found z. Now, the only way to get the answer for y is to use one of the original equations, because that's the only time we actually used y, right? So if I look back to my original equations, you can pick any of these original equations, doesn't matter which one. I'm just going to happen to pick the first one. So I'm going to choose the first equation. That's, oops, literally at random. You can pick any of them you want. And from here, I'm going to plug in my x and my z because that's the information I know. That's going to give me 2 minus 2y plus 3 equals 7. That's negative 2y plus 5 equals 7. I subtract 5 on both sides. That gives me negative 2y is equal to 2. Divide by negative 2, which means y is equal to negative 1. So that's how you solve a system. And like I said, there's many ways to do this correctly. You could have canceled out using this equation instead if you wanted to. I did this problem about 5 different ways, and I tried to pick the one that was probably the easiest to follow. So if you want to check your work, you would go through each equation and plug in x, y, and z, and make sure that both sides of the equal sign are equal to each other, and that's how you would check your work. So does anybody have any questions so far? We're going to do another example too. I know I can't see you guys in the front, so I always have to check. Alright. So let's look at example 2. So the first thing I recommend is to look through and see if there's anything I could add together that's going to automatically cancel out. What do you guys see so far?
Y.
the y's. Anything with the z's too?
Yeah.
Yeah, so there's actually a few choices here to do. You can pick to do one thing first or the other thing first. It's not wrong. I'm going to go with to adding the first and the third together. Okay, because I see that's going to cancel some variables out. In theory, you can add any equation to any equation, and it's still going to be correct. You might just not get any further, but you're not going to be wrong. So I'm going to add my first and my third. That's going to give me 6x. And what happens to my y's?
They go away.
And my z's?
Yeah, those go away.
They do, both do, right? And then that means 6x is equal to 18, which means x is equal to 3. So far we found the solution to x. So sometimes it's going to be easier than others. Now, in this case, you have a few different choices. From here, what you could do is, if I was probably doing this on my first attempt, this probably would be my instinct. I would go through and plug in all the x into each one, and then I would narrow myself down to a 2-variable system. But there's actually a little bit of an easier way to do this. Let's say that we add our middle equation to our first equation. What's going to happen when we do that math?
These are gonna go away again.
Yeah, the z's are going to cancel out again, so let's do that. And remember guys, I only have insight on this because I've tried the problems. So first time around, you're going to be thinking about what's going to work, and that's totally normal. So I'm going to add these two together. That's going to give me 3x plus 2y equals 15. So now that I have this equation, how could I go about solving for y with this? Good, I can plug the x in, right? So that's going to be 3 times 3 plus 2y equals 15. That's 9 plus 2y is equal to 15. I subtract 9 on both sides. That gives me 2y is equal to 6. Hang on, for some reason it's making me admit every student in my virtual. I don't know why.
It's because they're not logging in through the school email rather than the actual.
That's what it is?
Yeah, you're supposed to like log in through Clever, and then it'll automatically take you in. If not, they're gonna be in the lobby.
Oh, okay. Thank you. So from here, then we're going to divide by 2 on both sides. Now my computer's lagging. And that's going to give me y equals 3. And then our last step is to pick one of the original equations, any of them, and to plug in for x and y, and then solve for z, your last variable. So I'm just going to pick the first one, but that's totally random. So that's 2 times 3, my x value, minus 3, my y value, plus z equals 4. That's going to give me 6 minus 3 plus z equals 4. That gives me 3 plus z equals 4. I subtract 3 on both sides, which means z is equal to 1. So that would be the solution to your system. And once again, if you wanted to check your work, you could plug each of these back into the original equations. Anybody have any questions on this so far? Okay.
Wait.
Oh, sorry. I can go back.
Yeah, I just had a copy of the last one.
What is that noise?
I think the dog.
Cicadas.
Oh, they sound like a razor or something. It's so weird. Alright, are we good? Alright, so for the next one, first thing you always want to look at is there anything I can add together that's going to cancel anything out before I multiply by anything? No. Unfortunately, in this case, no. So, if you can't get that, my next suggestion is to find a variable that has a coefficient of 1. In this case, we have two choices, and that's the reality. We have the z and we have the y. And that's usually the easiest thing to multiply things by because it's going to be the easiest math. Now, the reason I'm going to choose y to deal with over the z is because I know that if I'm going to cancel out these z's, I'm going to have to multiply this whole equation by 8, and my numbers are going to get really big. Now, that would totally be correct, and you totally get the right answer. I'm just thinking in terms of simplicity, the simplest way I can do the problem. So, I'm thinking I'm going to try to multiply this equation by something to cancel out my y's. So, what can I multiply this equation by to cancel out the y in my first equation? Positive 2. I'm going to distribute the 2 to all my terms, and that's going to give me negative x plus 2y plus 4z is equal to negative 6. I'm going to then bring down my first equation. That's going to give me 5x minus 2y plus z is equal to 3. And I'm going to add these two together. Negative 2x plus 5x is (3x). What happens to my y's? Good. And then what's 4z plus z? Good. And lastly, we end up with negative 3. So far we have a two variable equation. We're going to try to make a two variable system by coming up with two equations that have the x and the z variable. So my thoughts are, what can I multiply my last equation by to cancel out the y in my second equation? 4. I'm going to multiply my last equation by 4, which will then allow me to cancel out the y in my second equation. So that's 4 times negative x plus y plus 2z is equal to negative 3. We're going to distribute. That's going to give me negative 4x plus 4y plus 8z equals negative 12. And then I'm going to rewrite my second equation and add them together. So what happens to my x's? What about my y's? And my z's? Equals negative 10. So does 0 equal negative 10? No, so what's this case? No solution. So does anybody in here want to do engineering in their future? No? You do a bunch of this if you do engineering. It's just like a really common thing. Netflix, this is what they use to basically come up with the algorithm for what predicts what you like. Like, you know how they say what you may like based on what you watch? This is the math behind how they actually do that. So, just a fun fact. Does anybody have any questions about this so far? Okay. Oh, I'm sorry, go ahead.
No, it's just, so just like one doesn't work, it's automatically no solution for the whole thing.
Correct. Yep. If you have one instance where you get a number that doesn't equal another number like that, you can rule out the whole system. Okay. And even if you did it differently, you'd also get a scenario like this no matter what way you went about it. So looking at the next one, I see that there's no variable that I can add together right away that's going to cancel anything out. So your next goal is to pick the one that has a coefficient of 1. That's going to be what we use to cancel out. So you can either go with the x or the z. What are you guys feeling? You want to go with the x? Alright, let's go with the x then. So we're looking at this first equation, and if we want to cancel out the x in the second equation, what should we multiply the first equation by? 3. Very good. I'm going to use the distributive property here. That's going to give me 3x minus 6y plus 3z is equal to 9. And then I'm going to line up my other equation underneath it. And then I'm going to add everything together. And you're going to notice that everything, it cancels out. And I'm left with 0 equals 0. Infinite. Now something I want to point out here, because like I said, there's so many different ways to do these problems. Say you dealt with the first and third equations, and you were going to cancel out the 4 by multiplying the first equation by a -4. That would have also given you 0 equals 0. So even if you attempt it differently, you're still going to end up with the same result. Yes?
Does it really matter what two equations you choose?
No. So you can technically work with either equation. I just picked these strategically to try to avoid fractions. So you could say I want to use this to cancel out this, and you can totally do it. It just might end up with fractions. Any other questions? Okay. So we're going to do a word problem. So it says here, you manage a clothing store. I had it written over here, but I lost the page. You manage a clothing store, and the budget is $6,000, and you need to restock 200 shirts. You can buy t-shirts for $12 each, polo shirts for $24 each, and rugby shirts for $36 each. You also want to have twice as many rugby shirts as polos. So how many of each type of shirt should you buy? So the first thing you always want to do are your let statements. So let's let t-shirts, the amount of t-shirts, be equal to the variable x. Let's let polo shirts be equal to the variable y. And let's let rugby shirts be equal to the variable z. And these represent the amount of each type of shirt. So when you're dealing with these type of questions, you're usually going to end up with an equation relating to money, and you're going to end up with an equation relating to the amount. So we know that we need to have 200 shirts, and those 200 shirts are going to be made up of a combination, a sum of t-shirts, polos, and rugby shirts. So I know that X amount of t-shirts plus Y amount of polos plus Z amount of rugby shirts is going to be equal to the 200 amount of shirts. Make sense? Now we're going to do our money equation. So I know that each t-shirt costs how much? $12. So I know that the cost of however many t-shirts I'm going to buy is going to be $12 times the amount of t-shirts I buy, plus $24 times the number of polos I buy, plus $36 times the number of rugby shirts I buy. And when I total up all of the amount of shirts I bought times the amount of money each one costs, that total should equal $6,000. You guys with me so far? Now, the last one thing we need to know is we want to have twice as many rugby shirts as polo shirts. So we know that the amount of rugby shirts, Z, is going to be equal to 2 times the number of polo shirts, because we're going to have twice as many. So now we have a system of equations. We have 3 of them. Now this one is not going to be easy to solve with elimination because of this situation we have. So I'm going to say we use substitution here. Like I said, sometimes that's going to be the case. So I'm going to suggest that we plug in 2y every time z occurs in the other two equations. So I'm going to plug in 2y into those other two equations where I highlighted in the pink. So when I do that, I'm lagging really bad right now. I gotta let it catch up. So I'm gonna replace my z with 2y. So for the first equation, that's gonna be x plus 2y plus, y plus 2y is equal to 200. So I just replaced my z with 2y. And then I'm gonna combine like terms here. That's gonna give me x plus 3y is equal to 200. Now for the other equation in blue, I'm also going to replace z with 2y. That's going to give me 12x plus 24y plus 36 times 2y is equal to 6,000. And once again, I'm just going to simplify and combine like terms here. So that's going to leave me with 12x plus 24y plus 72y is equal to 6,000. I'm going to combine like terms. I think that gives me 96, is that right? Thank you. 96y, and that's what I have so far. Now we have two equations here that have the same variables, so we can solve those as a system. Now you have the choice of course, multiplying this equation by -12 and canceling out the x's. However, that's going to give you really big numbers, but it would definitely work and be correct. My suggestion is to get x by itself here, and then we can plug in for x. So how can I get x by itself in the red equation? Not divide, but subtract. So to isolate the x, I subtract 3y from both sides. That leaves me with x is equal to 200 minus 3y. So now I see that my other equation has an x right here, and I know x is equal to 200 minus 3y. So I'm going to use substitution here. So that's going to leave me with 12 times 200 minus 3y plus 96y equals 6,000. I'm going to use the distributive property here. That's going to give me 2,400 minus 36y plus 96y equals 6,000. Combine like terms. That gives me 2,400 plus 60y equals 6,000. I subtract 2,400 on both sides. That leaves me with 60y is equal to 3,600. Divide both sides by 60, which leaves me with y equals 60. So far we know we need 60 polo shirts. So it's a lot, but we got it. So now I'm going to use this equation right here to find the number of t-shirts by plugging in for y. So that's x equals 200 minus 3 times 60. That's x equals 200 minus 180. That means x is equal to 20. So take a second to get this down if you need to, and then I'll scroll back up. Actually, I can zoom it out because I got to get back to the top. So basically, so far we know we need 60 polo shirts and we need 20 t-shirts. So to find rugby shirts, you have a few options. You can either know that the total is 200 and subtract away from 200, or you can plug into this equation right here for rugby shirts. So we know rugby shirts is equal to 2 times the number of polo shirts, which means how many rugby shirts are there? 120. And your answers should add up to 200, which they do. So that is how you do the question. And that would be your final answer right here. After all that work. So do we have any questions before we end?